All right, everybody. I hope you're doing great today. I hope you're excited about finishing your second week here and getting a week off from school. I want to go over some things that a lot of review, but also some of it's new. So we'll take a look at this here and let's get started. So the first thing we got to talk about, and we already sort of covered this, so I want to go pretty quickly through this. Remember, when you have a covalent bond, when the atoms are not very similar, they're going to be unequal. And if you remember right, the unequal sharing is sort of like the brothers that were my friend Mark and his brother Matt. It wasn't very equal at all when they were sharing their PS2. I can't remember anymore what it was, but one of those. One side sort of pulls on it, and it makes it a polar covalent. It's still technically sharing. It's still technically, both their gaming systems, but one of them definitely has the majority of the share. And again, that's going to create some sort of polarity, which you have this partial negative charge, and then the end that has that deficient is what we call a partial positive charge. And so hopefully there's nothing new on that. This is nice because it shows this from the standpoint of if you divide this out here, and if you look at that, the plus right here says that's where the partial positive is, and then the electrons are being pulled towards the right, towards the fluorine. And as you remember, probably fluorine was extremely electronegative. Most of the bonds, and again, I'm kind of skipping through this because while this is a great PowerPoint, it's a lot of review, and we've kind of tried to throw in a lot of review in here just because it's been such a crazy few weeks. But if you look at this here, it says the bonds are classified as covalent if the amount of transfer is just small enough or insufficient that it doesn't exactly have an ionic compound. So if you remember right, we had to talk about this, but in terms of numbers, and I'll get to that in a second, but it says if the sharing is unequal enough to produce a dipole, di meaning two and pole meaning unequalness, then the bond is classified as a polar covalent. Just a quick review, electronegativity is the ability of an atom to attract bonding electrons to itself. That's what we call electronegativity, and fluorine's king and francium is the least. So let's look at this right here. This is great. You can see up here how huge fluorine is and how small francium is, and it goes up this way. I really like this because it shows that. And if you remember, we have these numbers. So like, for example, fluorine had a number 4.0. And that really helps out with remembering as you take those numbers and you subtract them. So that's this next part here kind of goes through. And if it's 0, then it's pure covalent. It's a little less than 0.4. I think we use 0.5 actually in the PowerPoint. If I can skip, actually, you know what? I'll go ahead. Let me skip out of that. I'm going to discard that. If you go to, I'll pull this up. Remember, we went through this. I'm not going to present all of it, of course, but we went through this a few weeks ago. I think it seems like a few weeks ago, and we filled this out. So we kind of already covered this a little bit, but it's nice to look at it in a different context here. So let's get back to it here. And we were talking about how these numbers, which we've already covered, but it's a great review of everything. And so we got some categories, which we didn't talk about pure covalent, but we definitely talked about nonpolar, we talked about polar, we talked about ionic, and it's all about how big that difference is. And when you subtract them, you take the absolute value. There's no negative, it's just a difference. And so this is sort of what we looked at, and divides it up nice and gives some examples. So let's keep going and let's dive into this. And this is an awesome, I love this diagram right here because it kind of shows that range down here that we've talked about before. And I don't know why there we go. It shows it nice that in that range right there, you have this perfect symmetry. And by the way, a middle school standard in science is that if I can draw two lines, apparently I can't, if I can draw two lines of symmetry, X and a Y, and they're symmetrical, meaning the left and the right are exactly the same to each other, and the top and the bottom are exactly the same to each other. And what you have is a nonpolar bond. Obviously, ionic is ionic, and that's pretty obvious. But the question then comes, looking at polar covalent, we can draw that line of symmetry. Now, my Y has an issue, because if you fold over this side onto that side, they're not a mirror image at all. Of course, if you fold the top over the bottom, it is a mirror image, but if the X or the Y is not symmetrical, then that's when we know we got an issue. But again, and I'm not going to get into these numbers because we really don't cover it, especially in the crazy coronavirus e-learning month here. We probably wouldn't cover it in a normal time, but definitely not going to cover it here. But we talk about a dipole moment mu, and that's what measures the bond polarity. And again, we're not going to talk about the numbers. We're going to kind of do the eyeball test, kind of look at it and say, is this polar? Does it have a dipole moment? That's the question. And so, as you can see here, these kind of give you the dipole moments. Again, we're not going to concern ourselves with that so much. We do use the delta En, which we've already calculated a few weeks ago, by taking the differences between these two molecules. So the difference between H, the difference between F is 1.9. So what does that do for us? Well, this again just sort of shows that if we're drawing HCl, it's definitely, not only is the bond polar, so we look at the bond and we say, okay, the bond's polar, we know that, we can subtract it, but is the molecule molecular polarity? So we're kind of dividing this into two types of polarity, and this is a major point. You have the bond, is the bond polar or nonpolar, but then is the molecule polar or nonpolar? And there's really two ways to look at this. One way is to kind of do the eyeball test, like I said, draw your X and Y, and left is not the same as right. Top is the same as bottom, so that kind of tells you right away we got a net dipole moment, which means there's a huge difference. That means the electrons are being pulled this way. Let's look at this here. Now my eyeball test works again. If I draw my X and Y, they're all symmetrical. But on top of that, if I'm really trying to figure out, okay, the electrons are being pulled away from the carbon and away from the carbon, it's like some sort of huge tug of war, and the oxygens are perfectly equal strength, and the carbon's the rope, and the carbon's right in the middle, and it's creating this linear shape, which is again making it a no net dipole moment, which coincides with something that would be nonpolar. So even though this bond right here, if you did the math, and this bond right here, the bond would tell you it's polar. But if you take each one and you subtract them from each other, since one's going to the left and one's going to the right, it actually is confusing because the bonds are polar, but the molecule, again, that's the one we're focusing on today, the molecule is not polar. Let's look at water. Again, my eyeball test tells me something real quick. The top is not the same as the bottom. Now I can fold over the left and the right, and the left and the right, let me try that again, is going to be perfectly symmetrical. But really, if I look at this again and I say, okay, these bonds are polar, we can do the math test and subtract them from the table of electronegativity values. But the question is, what's the molecular polarity? What does water as a whole have? And as you can see, it's being pulled up, and there is nothing pushing it back down. So because of that, the most important thing we have is this middle line right here. It's showing that most of the electrons are being pulled out here, and that's because, if you remember right, there are two lone pair electrons on the top. When we draw the bent shape, we have that. This is a quick physics lesson. Now, I'm not going to go greatly into it, but example one, if you have two vectors going to the right, then you have a greater force, double the force going to the right. That's a plus 10. But there are other times, let's go ahead and skip example 2, that you have a vector going one way and an equal and opposite vector going the other way, and for that you get a 0. And that's what we really focus on when we're looking at this. What is the net? So looking at, now that we know geometrical shapes, we can tell you, okay, well, these two, a linear is going to always be nonpolar because they're canceling each other out. In this case, you have your bent, and why is it being bent? Well, remember, it's because of those lone pairs down there. So in this case, the molecule is always polar. You might want to take note of these as you're taking your notes. In trigonal planar, you have 3 different things being pulled at equal. So all of the charges, or all the forces, are going to pull in a very equal amount. So it's like that tug of war, again, nonpolar. Also, again, nonpolar. And then lastly, this one would be polar because that trigonal pyramidal, you have that lone pair of electrons and it's pushing it down. So in this case, the dipole moments of the 3 polar bonds is trigonal planar because they don't cancel out. All right, so this is what you're going to want to do. And you're going to want to look at things and say, okay, can I draw the Lewis structure? Hopefully you can. Can I determine the molecular geometry? Well, that's going to determine on a few things. Look at the bonds and see if they're polar, but think about it. If there are no polar bonds, then obviously your molecule is nonpolar. But then we might need to look at whether the polar bonds add together to get a net dipole moment. So let's do this real quick. So let's do an example. So one of the first things I'll draw, I have CCl4. So obviously I'm going to put the C in the middle, and that's the least represented, also the least electronegative. And I'll put the Cl and the Cl. And now the tough thing to do without seeing this or holding a model of it, which we're going to do something after spring break that'll help this, is basically this. These are it's a tetrahedral shape. So what's happening is all these bonds are perfectly spread out. But also remember, Cl is a big electron hog. So all of the dipole moments are being pulled out. So if you looked at these, Cl is just pulling them out. Of course, you have all of the unpaired electrons filling the octets here. We don't have to draw those, but basically carbon is just all the electrons are being pulled away from carbon. So it's losing the tug of war. And because of that, you have all of these dipole moments are canceling out. So this would be not only looking at this, we could do the eyeball test and kind of divide it out, but that's hard to do. But we would say this is definitely a nonpolar molecule because all 4 of the bonds added up cancel each other out. Let's do one more example here and see if we can get, let's substitute. We're going to do C, excuse me, we're going to try is the key word here. So let's try a new one here. Let's just substitute. Let's take an H and put it up here and then leave these CLs right here. And if you look at these CLs, this is still a tetrahedral shape, and it's still making a very similar case in the fact that these CLs are pulling out the electrons, right? And so that's going to show like that. But what's going on over here with this? Meaning, what is going on with, let's change colors, this bond right here. And what's going on is carbon's more electronegative than hydrogen. So if you added up all 4 of the charges, the directions of the charges, the actual charge is going to go down in such a way. And I'm trying to make that angle to show that it is a 3D effect. But this then would make our molecular geometry polar because those electrons are being pulled down to those chlorines. So hopefully this helped out with understanding the differences between bond polarity and molecular polarity. Also, I'm going to have on the agenda an opportunity to get in some Zoom meetings on Wednesdays and Thursdays, Wednesday and Thursday this week if you'd like. Check it out. I'll explain more if you understand it. Move on to spring break and and enjoy your brain break.